very great organizers for giving me this opportunity to speak. One of them is in the audio, is an organizer, and two others are Aditya Panigrahi and Anatoly Kuklov. And I will be discussing a version of the Kondo lattice model. Kondo lattice model is one of these eternal models of theoretical physics, which people have been working on for decades, and well, it has applications to real materials, to many real materials called heavy fermion materials. It's a difficult model to crack because it's essentially a model of strong correlations, which describes the situation when two completely different limits coexist. It describes interaction between itinerant electrons and localized electrons. Strong correlations are initially located inside of this localized orbitals where electrons create magnetic moments, and when the temperature goes down, the interactions between itinerant and localized electrons will either become stronger or die out, and we are interested in the outcome. So the kind of an old answer to the question of what happens in the end was given by Sebastian Doniak, who drew his phase diagram, which carries his name, and the answer is depending on the parameters of the model. We will get either Fermi liquid when localized electrons are kind of absorbed into the Fermi surface, or magnetic order where spins order and itinerant electrons kind of decouple. So and in the model I will be talking about today, we deal with a more exotic possibility when the spin subsystem has an interaction of its own, and this interaction transforms it into a spin liquid, and this and the cooperation and instead of a competition between localized and itinerant electrons, we have a cooperation which leads to creation of an exotic superconducting state with a fractional order. And I will explain what this fractional order means. Well, and the advantage, the additional advantage of our approach that we deal with a strongly correlated model in 3 dimensions. It's a 3-dimensional model, nothing one-dimensional, no better than that. Nothing. It's a strongly correlated 3-dimensional model, which nevertheless is analytically tractable. And this is basically the phase diagram. You see here is a exchange interaction Kondo coupling between equivalent and localized electrons, and this is a strongly modified Doniak phase diagram. On the left, where the exchange is ferromagnetic, the spin liquid and electrons are decoupled from each other. We have a Fermi surface. It's a Fermi surface of the electrons. On the right, when the Kondo exchange takes over, we go into the state of a Kondo insulated. It's Kondo insulated because there is in total there are 2 electrons per side, and this is like a small Fermi surface. This is like a large Fermi surface, which in the limit of 2 over full brilliant zone shrinks to 0, but in between lays this exotic superconducting state. But
why do you say large Fermi surface if it is
small Fermi surface is 1 electron per side, and spins are out of the Fermi surface. Now, you absorb 1 electron from spin, and it becomes 2 electrons per side, which is the Fermi surface grows, and occupies the entire brilliant zone, which is equivalent to no Fermi. So, yeah.
So, all of these solid lines are phase transitions or on the summations?
No, yeah, good question. Thank you. This is a crossover, and the only phase transition.
DC1 is the phase transition. Analyzing phase transition.
Also, so this is the phase transition for the Yao. Thank you very much. This is a phase transition for the spin liquid. I will explain it later. So, as I said, this exotic superconductivity, it has fractionalized order. So most of you are familiar with fractionalized excitations. These are excitations which carry part of quantum numbers of electrons. For example, spinons carry no charge, but carry spin 1 half. part of electron holds carry charge E, but no spin. Such excitations are known to exist in one-dimensional systems. And people speculate that they can exist in higher dimensions. But I consider it as a speculation. So now in our case, the spin liquid has this fractionalized excitation. The Majorana fermions is either spin 1. The difference between spin and either spin is that either spin is an internal index not related to Lorentz transformations. So, and electrons carry spin 1/2, and in our model, this excitations create bound states, and these bound states are naturally bosons. They condense, and what the fractional order corresponds to condensation of bound states of fractionalized excitations and electrons. And in the case we will consider these bound states between spin 1 Majoranas, which are neutral particles, and spin 1/2 electrons, which carry charge E, are naturally spin 1/2 bosons with charge. And this is a fractionalized order. So this is a plan of the talk. I will first describe the model of the spin liquid, and will because this is the main non-standard ingredient of our theory, then describe the Kondo lattice, and then we will get to the results. So the results are that we found a three-dimensional solvable example of a Kondo model, which has many, which combines many exotic properties. And it turns out that besides of fractionalized order, it also exhibits pair density wave and superconducting odd frequency pairing.
Can I ask you a question?
Yeah.
So what's the reason you take the Yali spin liquid model and not the plain Kitaev? For the plain Kitaev,
This will be explained in great detail.
because the exotic superconductor you also get if you take the Kitaev model.
But shortly, the reason is that with the Kitaev model is not tractable.
So just by having these extra orbital
Yes,
degrees of freedom, it's become.
yes. This I'm going to explain. So the
Sorry, what is tractable?
tractable, it means you can calculate by hand. By hand, not to stick it into artificial intelligence. When you stick it into artificial intelligence, it is not you. You're not in control. So now, let me tell you about this Yaoli model. So that this model is a generalization of the Kitaev model, which many of you may be familiar, and it can be solved by similar means, by a reformalization of the spins, and the basically in the fermionic language, it will be like three replicas of the Kitaev model, but the most essential difference for us that in the Yaoli model, physical spins are local in terms of Majorana fermions, and therefore, what will happen as you know, in many versions of the Kitaev model, these Majoranas are gapless, but in order to flip spin in the Kitaev model, you need to create a gauge field flux, and it costs energy. Therefore, despite the fact that the elementary excitations are gapless, the spins in the Kitaev model are gapped. And this makes them very unresponsive to perturbations. If you take Kitaev model and add itinerant fermions, you will need strong coupling in order to have any effect on the Kitaev model. That's make such more wow. This is difficult to deal with, but in our case, well, this psi fermions will be gapless, and spin excitations will be gapless as well. And so what happens that when exchange interaction with conduction electrons creates bound states of electrons in this spin 1 Majoranas, and this interaction dynamically generates a hybridization matrix element with the conduction electrons. And this hybridization matrix element is essentially a charge E spin 1/2 boson, and it's fractionalized order parameter. And this will be a superconductivity without pairing. And actually, we suggested this mechanism with Pierce exactly 30 years ago. So we, and Eduardo. So we have to celebrate it as well. So now that's the Yaoli model Hamiltonian. It's on each side of a lattice with coordination number 3. It's important that coordination number must be 3. There are two kinds of spins, spin sigma and spin tau. So you can think about them as spin degrees and orbital degrees of freedom. Tau spins interact as in the Kitaev model. So, for example, along this bond, the interaction will be tau x, along this tau y, along this tau z, tau z. But sigma ones interact isotropically like in the Heisenberg model. And this Yauli model is solvable on any lattice with coordination number. But the spectrum for different lattices will be different, and we will take a very particular lattice, which is called hyper-orthogonal lattice, three-dimensional, and the distinct feature here will be that the fermions will have a Fermi surface. That's what we need to make the model tractable. Now, how to solve the Yauli model? Here we follow this people. The approach is referminization. You can reproduce all commutation relations between Pauli matrices, writing them down as byproduct of Majorana fermions. So the Majorana fermions are like gamma matrices. They are real. So psi dagger is equal to psi, b dagger is equal to b. So they anti-commute, and in order to fix the irreducible representation, you impose a constraint on the Hilbert space, but saying that this product of all six Majoranas is equal to 1, and the advantage is this constraint commutes with the Hamiltonian, and because of this constraint, the product of sigma and tau, which would be from one hand, it's a product of 4 Majoranas, but because the product of the 6 is equal to 1, it's equivalent to the product of the 2. So you substitute this into the Hamiltonian, and this Yauli model becomes this. And now what happens that on each link on this link bx lives. On this link it will be dy dy, and these products commute with each other, and you and this model effectively becomes model of 3 Majorana fermions living in a static Z2 gauge field. That's how it works. So in the ground state, the ground state is defined as follows. These fermions choose the gauge field configuration in which they can propagate free. And it has been shown that for this hyperorthogonal lattice, this ground state configuration is simply that all these gauge fields are equal. So therefore, for sufficiently small temperatures, essentially this model is equivalent to the model of non-interacting variable. That's how it works. Well, here it is just an illustration of some details of the diagonalization of the Hamiltonian ironic Hamiltonian on this hyperorthogonal lattice. There are four sides in a unit cell. So now, what is Majorana Fermi? It's a real Fermi. It's a Fermi version of a phonon. The phonon field is real, right? So it means that B dagger K is equal to B minus K. And the same with the Majorana fermion. When you go to K space, you can introduce creation and annihilation operators. Your creation operator will be equal to annihilation operator. Creation operator for K will be annihilation for minus K. So in other words, you can say that Majorana fermions are like ordinary ones, but occupying a half of the brilliant zone. You can arbitrarily, in an arbitrary fashion, cut your brilliant zone into two mirror images and work in one half only. Now, I have to mention that you can omit this Z2 gauge field at temperatures which are much smaller than a phase transition. There is a very interesting phase transition in this model, which nature we don't exactly understand because we don't know what the parameter is, but we know from studies done by other people that below the temperature, which is of order of 1%. I think there is a mistake here. It's an extra zero. About 10% of this key type interaction, the gauge fluxes become rare.
What is the flux gap? What is the value of the gap?
0.1 K.
1.8.
Yeah. K is this key type.
But the ordinary temperature is 0.01.
No, 0.01, 0.01. I'm sorry, there is a mistake here. Extra zero.
So what's the, okay, there is a difference, of course, between the Orly model and the Kitaev model, but it's also a crucial difference that you are not on the honeycomb lattice. So if you
No,
take
just a second. There is a class of models.
yes,
We have taken one particular lattice. Kitaev model can be perfectly well formulated on this hyper octagon. You who can solve it. It will be the same spectrum. The difference in the excitation spectrum is just Yauli is 3 times the J.
yes. But my question is, if you take the Orly model on the honeycomb lattice, do you also get a finite temperature transition, or is it a crossover?
A crossover. The difference is not in the dimensionality.
Okay, that's my question.
In 3 dimensions, either for Kitaev or for Yauli, there is a thermodynamic phase transition from confined to the confined phase.
Yeah,
Right. So now, for this particular lattice, we have a Fermi surface of Majorana fragments, and that's what is important for us. Now, let me repeat again the final slide about the Yauli, that the excitations propagate in Majoranas, 3 species, static Z2 gauge field fluxes. At final temperature, the fluxes are thermally excited. They generate mean free path for the Majoranas. They actually act as a static impurities. In 2 dimensions, this may be a problem. In 3D, it is not, because there is a phase transition separating the high temperature phase of deconfined fluxes from the low temperature phase of confined. Now, just another thing about this for high temperature, you can spin excitations become diffusive at small temperatures because there is the fluxes act as static impurities, and at small frequencies and momenta basically the spins become diffusive. But this is well. So the most difficult step is taken. The strong correlations in spin liquids are taken into account exactly. So now we can add another ingredient to our cooking, which is itinerant electrons, and we introduce them in a very simple way. We put them on the same lattice. So they hop on the same lattice, and on every side they interact with this sigma spins of the Pauli model by simple exchange interactions. And as I said, if this interaction is antiferromagnetic, it will create one other important thing. We look at the band, electron band is half filled. So one electron per side, one spin 1/2 per side, and this orbital big degrees of freedom are absorbed into the Zippel field, which at small temperatures actually gives you just small convections. Now you can more or less forget about this gauge field, and this interaction will create bound states between Majoranas and electrons, and this will lead to a superconductivity. So how do you see it? You substitute for S for this sigma, you substitute a bilinear in Majorana fermions, and it naturally factorizes in this kind of order parameter C, which will be 2x2 matrix. And we have taken this special limit of a high field band when the Fermi surface of the electrons is the same as the Fermi surface of the Majoranas. And in this case, the bubble diagrams, Majorana electron bubble diagrams, are logarithmically divergent as for BCS theory or for a Piles theory, and you can sum up the leading bubble diagrams and get singularity and the phase transition. Everything like in the BCS.
It's justified to make this assumption. I mean, if you look at the Dirac
Which
case,
assumption?
that the Fermi surfaces are the same. I mean, if you look at the
No, it's just my wish.
yes, true. But if you, for example, look at the Dirac case, the Fermi velocity of the real electrons will be vastly different orders of magnitude from the velocity of the Majoranas. And
Just a second. If the Fermi surfaces are the same, you can allow the velocities to be different. The logarithmic the divergence will still be there. It is just the coefficient that the log will be affected. Nothing else.
But you need to tune, in other words, an infinite number of parameters, right?
Why
To
infinite?
get the same Fermi surface, for the conduction electrons.
No.
I mean, in principle, yeah.
No. This model, there's no tuning needed. Just hopping. No other tuning. Just nearest neighbor hopping.
Oh, I see. So
Nearest neighbor hopping. So it's a little bit like a Piles instability. It only occurs when you have nearest neighbor hopping and the hop filling. but it does occur.
And nearest neighbor for both. I mean, so you have identical lattices for the two systems.
Yeah,
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 nearest neighbor.
yeah,
So it's a proof of principle. Of course, the real world is never like
Well,
that.
if you want the infinite number, it's all the other topics that you are setting to.
But the point is, it's exactly solvable at this point.
Yes, but I mean, like, you are assuming that all the other topics, the longer range topics are zero.
Yeah, like the Lyell's transition, if you make the nesting disappear, it disappears at zero cut.
But
Okay. That's the
in
point.
one, the nesting is a generic feature. Here, you know, to have this logarithmic instability, the two sperm surfaces to be identical, that means.
but,
Yeah, but the point is-
just a moment, it just comes from here. If electrons are on the same lattice,
Yeah, and also nearest neighbor hopping for both.
nearest neighbor for both. of them. Yeah,
Just to clarify the consequence of what we just discussed, when you're away from hard pinning, your Eppel star goes down all the way to Newton, is it right? There's a finite region at small j where you have Eppel star.
if the nesting is not there, you will need finite coupling to get instability.
But you may have another, it's very difficult.
Wow.
I mean, it's not clear that you would have this phase. If,
Well, then everything becomes non-universal. If you need finite coupling to do anything, everything becomes non-universal. And interesting, now essentially this is your mean field Hamiltonian now, and you can see that now this psi and psi are Majoranas. So you started with two Dirac fermions in the band, and it is equivalent to 4 Majoranas. And naturally, there are only 3 in the spin liquid. So 1 Majorana from the band is left as an orphan. And the spectrum of Bogolubov quasi-particles now will include 1 orphan mode, which remains ungapped. 3 others will hybridize with the spin liquid Majoranas, creating a superconducting gap, but 1 band, 1 Majorana mode from the band will remain gapless. So this is that's a superconductor with a finite Sommerfeld coefficient in the specific. So these are just some expressions for the Hubble diagram. You asked about the different velocities. They're there. You see if K and T are different. It affects this Hubble diagram. The instability, the transition temperatures determined by this standard expression when J times the Cooper loop is equal to 1. Now, another interesting piece. This other so-called order parameter V is, as you might notice, it's not Z2 gauge invariant. The Z2 gauge invariant is electron self-energy, which contains two charge E order parameter. So this object which is Z2 Z2 gauge invariant, and it will the interesting part here is that the Fermi surfaces of electrons and Majorana fermions are nested, but they are located at different parts of the Brillouin zone. The Majorana Fermi surfaces centered at this P point, but the electron one is centered around the gamma point. And for this reason, the sign of this object at different different sites inside of the unit cell will be different. It will the sign will alternate from one side to another inside of the unit cell, and in that sense, it is a pair density. The sign of this V boson. So that's again the story about the electron self-energy. It contains the normal part and the anomalous part, and they can be characterized by 3 mutually perpendicular unit vectors. These objects are gauge invariant, but they're made of two V quanta situated at different space-time points. So this is essentially the fractionalization. V itself is not gauge invariant, but the gauge invariant object is made of this quanta which can be arbitrary at arbitrary distance in time and space. That's how the anomalous part of the self-energy looks like. You see it's like a triplet superconductor, but there is a piece which is odd in frequency, and there is a piece which is odd in momentum. This I and J correspond to sites inside of the unit cell. Now, I think I have almost finished just few things about finite temperatures. As I said, at finite temperatures, but below this gauge phase transition, the fluxes are thermally excited and can be treated as static scatters, as impurities, and you can use the standard impurity technique developed for impure superconductors in, I don't know, 60 years ago, in order to see what kind of difference it makes. Curiously enough, this static scatterers have two different effects. They introduce finite mean-free path for Majorana fermions. The Majorana-Green's function now contains this piece, and they also modify the interaction vertex, modify the exchange contact interaction, making it effectively frequency dependent. And what happens, actually, they enhance this contact interaction. It's an interesting effect when the excitations become diffusive. They spend more time near the interacting speeds, and this effectively enhances the exchange.
Can I ask about this static
But
part? So only in the Yao-Lee model, isolated Yao-Lee model, the Z2 fluxes or Z2 gauge fields are static.
yes,
Once you switch on the Kondo coupling, they acquire dynamics.
no.
Yes.
It can be with the four Hamiltonian.
Not if you have a
In the
full Kondo.
Kitaev
No.
model, that's true, but in the Yao-Lee model, they can meet with the four Hamiltonian.
Even with the full
Yeah.
Kondo.
Absolutely.
Yes,
that's the whole point.
Yes.
Yeah.
Nice.
Actually, you can deform your Yao-Lie model a little bit, making them the dynamical, and see what consequences it may have. I just don't think I have time to discuss it, but we don't need to be so rigidly in this exactly solvable case. So they change the transition temperature a little bit.
So I didn't understand. So you're saying this is similar to Anderson's theorem? There's sort of a, it's not even cancellation. You say is it increasing? You said T is increasing?
Yes. Well, it changes the transition temperature. Yeah.
T is equal. And the second question is, so here the disorder is No, it's not quench disorder really. You're averaging Z.
It's not quench disorder.
So, but this doesn't have a, you just do the same diagram, so it doesn't have any.
Yes, I think it's the same. The only difference with unquenched different internal need into the dash line, for small concentration of these impurities, it will not make much. Oh.
15 minutes left.
No, okay.
I mean, now we have 20 minutes.
So I think I conclude my talk, and so we have an analytically treatable Kondo lattice model which describes a plethora of phenomena usually associated with strong correlations, and all these phenomena such as high density wave formation, odd frequency pairing, or the parameter fractionalization are facilitated by the emergent gauge fields of the underlying spin liquids. Well, this indicates how crucial it is for us to understand spin liquid physics. That's all.
Okay, so plenty of time for questions.
Nice talk. You said that what you require is a trivalent lattice. Is the lattice part of that necessary? Do you need periodicity, or could in principle you have a three connected graph?
I don't think we need periodicity. Of course, for this particular solution, we need periodicity. But in order to play with this, the model is still equivalent to static gauge field for plus fermions on any lattice with coordination number.
Then following this up, if in a different lattice, the ground state might not be the equal flux on every bond.
Yes, there are such lattices where it is not the case. Yeah.
Would it affect the rest of the treatment? I didn't think.
Well, yes. First of all, we needed a very special lattice where Majorana's have a family. I know only one other example. I don't remember how it's called, but it's equally complicated to three-dimensional lattice. So I know only two examples.
Questions? I'd like to take back to Frank's question, actually. So you say it's important to understand the spin liquid, but actually what was crucial here is that your spin liquid was not modified by the interactions. There was no self-consistent modification of its behavior. Can you say more about what sort of conditions you think that would work in? And you said you had some things you could say, we didn't have to.
Well, we looked at two deformations of this Yau limit. First of all, you can add the Heisenberg exchange, and you can add the Heisenberg exchange of orbitals. This one is relatively harmless. Because for small Heisenberg exchange, it's just a modification of the spectrum of Majorana furniture, you can deal it with perturbation theory. And only for for strong JH comparable for the Kitaev interaction, it can magnetically order signals. The orbital exchange actually makes the gauge fields dynamic. But again, we looked at the example of hexagonal lattice, and what we found is that for this orbital exchange makes the field the dynamic, but still does not kill the Weisen gap. And I guess that if the Weisen gap is there, you can still play the same game we played but basically you can live with the dynamical Z2 field provided the corresponding excitations are gapped.
But what happens to the Fermi surface?
What
The
happens?
Fermi surface. So,
No, really, not
so it doesn't get distorted, or, I mean, like,
well.
it will be unstable.
Okay, just if they're gap, you can take still can take the fluctuations. You using the perturbation.
Yeah, but I mean, you will get at least a distortion of the Fermi surface,
You will get a
which will affect
at
your.
finite temperatures. You will get a distortion of the Fermi surface, which will be exponentially small in temperature.
Why exponentially small, so you mean this
No,
one?
no, because your fluxes, to excite your flux, you still need an age.
Yeah, but you have Victor process, I mean, you are allowing.
It could be second order.
Second order
corrections,
right?
Oh, second,
Yeah.
well, yes, yes, true.
That will affect the nesting angle.
It will affect the nesting angle, but for any okay, yes, it will affect the.
Yeah, that's what I mean by fine-tuning.
Mhm.
There's a question here, question.
Yes, this is very interesting talk. So I'm wondering for the remaining, for the leftover Fermi surface, whether this fluctuation could induce superconductivity. So there is a there is a leftover Fermi surface.
Left
So
over.
could this
Ye-
fluctuation induce
ye-
actually carry for that leftover
Ah,
and create another.
just say,
Yeah,
well,
that's right, yes.
no. This is a Majorana. This is a Fermi surface for a neutral Fermi.
Okay.
For a Majorana.
So
Fermi.
he raises an interesting possibility that you might have further instabilities of that set.
Yes, but
This one's got this, presumably it's could get some effect. from
Uh,
fluctuation.
people have looked at this kind of instability, but it will be very difficult because this Majorana is like in the icing mode. So you need long range interactions in order to create any other parameters from this, because
I was wondering about the meaning of this charge E superconductivity. So when you have a vortex in V, clearly that is carrying H over E flux. and the full vortex in V, since the thing is only charge E, it's H over E. But can I also have half vortices in V and then sort of put the minus sign into the Z2 part so that ultimately the fundamental excitation is H over 2E?
Yes, you can.
So it's H over 2E. It looks H over 2E if I do, or if I do, let's say, little parts, how does it look?
Pierce can answer your question.
When you arrive in Wisconsin, you will be able to work with a young man who's been thinking about this.
Oh, okay.
This at the moment. And it's not so, it would be very nice if there were a clean prediction here, but there's, as Tsvelik has thought about this also for chargey, autoground is another context. When you have a bison around, it loves to sit in the middle of an H over 2E vortex and heal it. And so under normal circumstances, the H over 2E vortices would be the lowest energy configurations. But there it does leave open the possibility that at higher fields, that the H over 2E vortices might bind together to form H over E vortices. And I think Alexei has something else to say about this.
Yeah. Now, what we have done, we looked at the Ginzburg-Landau theory for a simplified version. Well, our other parameter has SU2 symmetry, and we are reduced to U1. And in the ordered state, you still have this Z2 gauge coupled to this product of other parameters and the plaquette. So it turns out that this is your phase diagram extracted from Monte Carlo, and this is essentially a dehiscenoid phase, and there is an evidence. There is an evidence for two kinds of order. One would be 2E, and the other is E.
Any remaining questions before lunch?
Just one, I don't know, probably you said it, I missed it. So in principle, I mean, could you, from this half filling chemical potential for the conduction electrons, could you perturbatively treat small deviations in the Fermi surface?
Small deviations, of course. Well, it's like small deviations from nesting. So, as far as your exchange in interaction is much smaller than the Fermi energy, you're fine. So small deviations from nesting will shift will introduce finite threshold for the exchange interaction. As soon as this threshold is much smaller than the Fermi energy, you're still in the range of the perturbation theory. And this actually is the answer to a question about the deviations from this. Any deviations from nesting will mean that you need a finite exchange interaction to create an instability. If this threshold is much smaller than the Fermi energy, you are still in the range of the perturbation theory. You can still
But you may have a competing.
select. Yes, you you may have something competing this product.
Okay, last question before lunch.
One question on how exactly, I mean, at which level of detail you define temperature effects? So is the dominant contribution actually that you get some lifetime for the from fermions? And you get some certain lifetime from present of fluxes to be microscopically model the fluxes. How is essentially phenomenological parameter that model?
No. The tau is not a phenomenological parameter. It is the fluxes act as resonant scatter. And actually they're in the unitary limit. But the concentration is small.
Single scatter
Yes,
solution.
yes.
Ingredient then is somehow the activation energy for individual fluxes and the scattering behavior of fluxes.
Okay, let's thank Alexei for a fascinating talk.
And we resume in an hour and a half. Let's do this.